This is the title of my talk, and I will not take much time for the motivation talk. It's obvious that correct propagation problems are very important for the industry, and especially for extreme states, which are now part of the modern technologies. I just want to remind to all of us that we still don't have engineering standards for extreme states and for dynamics, and this creates a gap between the academic understanding and engineering applications. And I'm going mainly to talk about the unstable behavior of parameters controlling the dynamic crack propagation, and about an approach which helps us to deal with these instabilities and to actually simulate them. And at the end of my talk, I want to show a beautiful analogy which allows us to interpret this instability, and came to the conclusion that these instabilities are actually natural, and they just can be easily understood. And let's get started with the classic fracture mechanics, which is based on the energy balance equation, which leads, when we apply this approach to the crack propagation problem, which leads to this equation, which represents the relation between the current stress intensity factor and crack velocity. So if we put this Williams expansion into the energy balance, we will derive this relation that gives us the possibility to connect the energy flux and the crack velocity. This is a classical approach, well-known approach, and it can be reformulated in terms of the crack intensity factors, and that means that in these terms we will have these right parts of our relations that are dependent on the strain rates and the velocity, crack velocity. And so the classic approach can be summarized to these facts. It predicts that maximum speed that crack may attain is a Rayleigh surface wave speed. It follows just from the previous relation between the energy flux and the crack velocity. It indicates the unique relation between the crack driving force characterized in terms of the dynamic stress intensity factor and the crack speed. And the classic model and the majority of its modification include rate dependencies considered as material function. So the static value is just substituted by the complicated functionals. For example, K1D, which is supposed to be dependent on the crack velocity, and to a material property. But is it the fact that it appears to be a big question? And so there are some examples of different views on this matter. I just used this, the most classic works, the most famous scientific groups. So the first one, Irwin and Daly and some other research groups, they tried to establish this KV relation as a smooth and continuous relation for some of the materials. The group by Professor Kharkov and other research groups, they found that these relations is actually not unique, and it depends on the geometry of the samples. So there are two samples for the same material. They will show us very different relations. And the group of other scientists that can be represented by this series of these papers, they came to even more dramatic conclusion that actually there is no dependence between the energy flux and the crack velocity, so that they observed these straight lines, when the energy flux or current stress intensity factor has is characterized by the large variation when the crack velocity is almost constant. And so another premier, so the example of instability is the crack velocity oscillations. So it is, can be represented, for instance, by the investigations of Professor Feinberg. The best known result, and an interesting moment that the crack velocity exhibits unstable behavior, and this instability they observed after the certain critical point, after the critical value of the crack velocity, crack propagation. And so another example of crack instability can be observed even during the start of the crack propagation. So it is more or less clear that experiments on the measuring of K1D or starting value of stress intensity factor would give us very different values. Even for the same material, we can observe K1D that are bigger than K1C or less than K1C. And it was discussed also in numerous works. There are the most famous of them. The work by Scholke, Ehrlich, and Kharkov about short pulse fraction mechanics. They definitely established that for many materials, K1D can be less than K1C. The post view that K1D is always bigger than K1C. And for some cases, even non-monotonical behavior of K1D is observed, like in some papers by Professor Kharkov, when he measured the non-monotonic behavior of K1D with the strain rate, which first became less than K1C, and then it goes up and greater than K1C. We can deal with these effects if we take into consideration some characteristic times, and this is an approach we are developing in our research group. This approach is essentially non-local in time and in space, so it is based on the special temporal and spatial temporal representative volume, and we consider the minimal fracture event, the minimal crack jump in our case, which is described by the D parameter. It's a linear size. In this way, fracture scale level is set, and we consider the crack initiation when we go to the crack grow initiation a problem, we just can simplify this approach just and reduce it to this simple criterion. This is the result of application of this approach to the problem of crack growth initiation. We can see that for the K1D, we can, this yellow region, it designates the possible values of the dynamic fracture toughness. So that for the threshold loading, for the threshold pulses of fixed duration with the minimum amplitude, we can get K1D less than K1C, the lower boundary of this yellow region. And if we keep our load acting up to the moment of fracture, then we will get this upper boundary and K1D bigger than K1C. So no need for modification constant into material functions. Only two constants can be used, utilized just to get all these effects. And so there are, let's consider examples of application of the same approach to the crack propagation problem. We consider two problems: the quasi-static loading, which was realized in these experiments, and the problem of impact loading in larger big plates realized in the experiments by Ravich and Knaus. The problem can be stated as a linear problem. A small deformation are considered, and no any complicated rheology can be used when we consider just a linear elastic problem. This is a simulation technique, and the way we release the nodes according to this fracture criterion. And first, the crack velocity in the experiments by Ravich and Knaus can be simulated, and this is a result of this simulation. Just in frameworks of just linear fracture mechanics and the linear elasticity and the above-mentioned criteria. We also observe numerically can observe this oscillation of crack velocities when we have a mean velocity that is formed by the crack jump on the distance d. We consider the mean velocity of this jumping. It also oscillates like it is shown here, and even the critical point where this the amplitude of these oscillations became essential also can be observed here, approximately the same value. Applying the same approach to samples with different geometries, we can get different KV relations. This is our endeavor to simulate Professor Kartkov experiments. And the most interesting thing that in the case of semi-infinite crack and large plates, we get this kind of relation between crack velocity and the energy flux of current stress intensity factor. We cannot get in quantities exactly what was observed by Ravich and Knaus, but we have this instability in the form that crack intensity can exhibit a larger, rather big variation, while the crack velocity is constant. And so both cases can be simulated. The smooth curve and this phenomenon observed in the experiments by Ravichander and Knaus. And what is between? Between is what is between. If we are coming to quasi-static load, then the small variation of current stress intensity vector is observed, and then we can apply the classic curve if we neglect this variation. But when we have a pulse load, then this variation becomes very essential, and no classic dependency between V and K is observed in this case. And now I just want to show the simplest analogy which allows us to understand all these effects. And this is an analogy with the fracture of simple linear oscillator. If we have, here we have, on the left we have oscillator and the correct initiation problem. And both cases can be analyzed analytically if we have the simplest state of the problem in the case of correct initiation, the semi-infinite crack and the larger plate, then all the relations can be obtained analytically, and we just try to analyze this possibility. And in the case of the oscillator, easily the rate, strain rate, the strain rate effect can be obtained. It's like that. This is a critical force which depends on the rate of applied load. And here is the dependence between the duration and the fracture time. They are strikingly similar for the crack and for the oscillator. And this curved dependency corresponds to the fracture delay, to the amplitudes which are close to the threshold amplitude. In this case, we observe the fracture delay, so that fracture occurs on the decreasing stage of the load. Same thing observed in experiments with macro cracks. This is the same effect Kharkov and Kharkov discussed many times. And this, the relations between duration of the applied load and the amplitude for the crack and for the oscillator. And we see that the upper curve corresponds to the case when we have no delay, and the lower curve, this is a fracture, delayed fracture. And the load momentum is just the square of this rectangular, also can be calculated for both cases, and they are strikingly similar for the crack and for the oscillator. So the upper curve corresponds to the case when we keep on the applied load up to the moment of fracture, and the lower curve corresponds to the threshold amplitudes when we always have fracture delay. And if we adjust these minimum points for the oscillator and for the crack, we can just associate the oscillator with the crack, with the macro crack, and we can get the natural frequency of the oscillator. It's about 300 kilohertz for the particular materials studied by Shoki and Kharkov. And here we applied this oscillator model for the small fracture when we considered the sample as a bunch of oscillators. And we simulated the appearance of the sporing crack. And this model is not very complicated. Our bunch consists of 3 oscillators and 5 oscillators. In both cases, the rate dependency can be simulated and obtained, and also delayed effect, the effects of fracture delay also can be obtained. There are comparison between observed in experiments and calculated by this oscillator model. And so, conclusions. So we can consider crack propagation at stability of crack propagation in frameworks of the approach, which is based on the taking into consideration these characteristic times. And the main thing I want to say now is that if we can use this analogy, we can have this black box, and we can put in this black box macro crack or oscillator, and coupled with the pulsed Lloyd, we cannot distinguish them judging on the dynamic fracture effects. And so it's a very interesting analogy, which probably would give us an opportunity to understand this seemingly complicated dynamic fracture effects on the basis of some engineering viewpoints. Thank you.